Let's talk about the Newton-Cotes formulas. What did we do so far and what will we do in that video? First, we learned that theorem. You can find weights omega k for these monomials, and if you found these weights, you can use them for every polynomial of degree m, and on top you can use it for non-polynomial functions by applying that. How did we find the weights? We talked about that in our first video. First the proof for the theorem, and then we said, okay, let's use that matrix, let's use that right hand side, and then we can find these weights. We have a system of linear equations, and so we can solve that system best if we use a computer algebra system. Okay, and if we do so, we get this tabular. In the German version of Wikipedia, there are also lines for 9 and 10. And then we can use these weights. So from the point of an engineer, from a point of a non-numerical guy who uses numerics but does not want to invent something new, then you need that tabular, and you don't need to know how this tabular comes into life. But we are in the lecture about numerics, and so I also want to give you the background information, and so I did. So this theorem is not important for us, so we can skip. And now this is how we apply these formulas for an approximate value if f is a non-polynomial function. That we did in the last video, and also we split it. Here is an example without a split, and here is an example with split. We did another example in our last video. And now we come to the implementation. Okay, let's start with Newton-Cotes value here, and the user tells which degree of the Newton-Cotes tabular he wants to use. That means which line shall we use. In our tabular, I think that was the letter n, so don't be confused. This n is how many parts shall we generate. In our last video we generated n is equal to 4 parts, and we used degree 3 values. Okay, so this is the implementation. First, here we have the interval a, b. Then let's say we split into 4 sub-intervals. That means n is 4 in that situation. And then we use some degree, and maybe we use degree 3. And that means that we use that point, and 2 intermediate points, and here again, and here again, and here again. And so we will evaluate at these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points. 13 is the same as 4. N is 4 times degree is 3 plus 1. And that's why we have that. And then we have the weights. In that example, the weights are 1, 3, 3, 1 for that part, but then a 1, 3, 3, 1 again for that part, 1, 3, 3, 1 for that part, 1, 3, 3, 1 for that part. So here we have a 2, here we have a 2, here we have a 2, but here we have a 1, and here we have a 1. So let's go to that line. Degree is 3. So let's take the first value times 1 here, then 3 times these values, this one, this one, this one, and this one, and 3 times these values, this one, this one, this one, and this one, and then 2 times 1 times, that is this, here, here, and here, and then the last point, this one again, only 1 times. And then let's divide by 8, and what is missing? Missing is the multiplication with the interval length, which is in that case the length of one part, and so this is b minus a divided by n. It was 4 parts, so this is the length. And then we have the integral value from here, and we scale that integral value. We adjust it by the length of the intervals. Okay, this is the implementation, and this is the implementation for degree 1, which reproduces the trapezoidal rule. This is the reproduction of the Simpson rule, and then 3 till 8, the Newton-Cotes rules. Okay. Normally a user does not prefer that kind of function, so we embed that. This is our function. We embed that in our code. We also used for trapezoidal and Simpson, and so this is a complete copy of the code we had, except of that line. Okay. And then we can run that code, and in the script we have an example how to use that function here, and another example here. Okay, now I want to show you my test of the functions, and for the moment important is that degree times n. This is important because we want to avoid an unfair competition. So this is how I want to compare the code. Let's focus on these lines here. First, I'm using our function, which we used a lot of times before, function 1, and this is that function. It's the constant 1 function on the interval from 0 to 1, and it's the function absolute of sine of exponential, and that will produce a function which is continuous on that part, but there are kinks, so the derivative is not continuous. That's the type of function, function 1. So what do we do? First we have the integration interval. Here I used 0 and 3 plus something because I want to avoid the following situation. If this is the integration interval, and here we have the constant 1 function, and then our function looks like that. Here are the kinks. The first derivative is not continuous, and here is that jump. And I want to avoid that by splitting the interval we come in the situation that we exactly split at that position. Okay, so I extended here the interval, and so we will never come into that situation. This is for finding the correct integral value, and so I will split the integration interval. Let's run the code, and then I give you additional information. Okay, this is the function. Here is the position of a kink, position of a kink, position of a kink, 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 kink. 1, 2, 3, 4, 5, 6 kinks. And I want to split the integration interval, integrate from here till here, integrate from here till here, integrate from here till here, from here till here, from here till here. This split is a very good idea, because on these parts the function is infinite many often differentiable, and that improves the quality a lot. So if you know there are kinks and you know the positions of the kinks and the jumps, then always split the integration interval, and that's what I do. And due to the nature of the function, which is sine of exponential of x, I can easily solve the equation where is that function 0. When does the sine produce a 0 value? It produces the 0 value for multiples of pi. And when does exponential gives us a multiple of pi? This is at the logarithm of k times pi. So this explains that. So I want to subdivide the interval in these parts, and please remember this trick. if you have a function which is problematic at some finite many points and you exactly know these points, then always split the integration interval. So then the total integral value I get by splitting into a lot of sections and then adding up the integral values. So this is the correct integral value, and then later we can compare the results of our algorithm with the correct integral value. Okay, here we plot the function, and then I'm using all degrees from 1, which is the trapezoidal rule, till 2, Simpson rule, and so on. And then I get a result, the answer here. And here I'm using the degree, and here I'm using the number of parts. I adjust this number, 840 divided by degree. Why? Because we evaluate the function at the multiple of these two numbers, so the comparison is a fair one and not an unfair one. It does not make sense to compare two algorithms and one of them gets more information about the function. Calling the Newton-Cotes formula, we evaluate exactly at these positions, degree times n and then 1. So degree times n, if this is a constant, then for all degrees here we evaluate the function at the same number of points, at the exactly same points, and then the Newton-Cotes formulas use a different combination of weights. Sometimes one function value is multiplied with, let's say, 1 divided by 3, and the other time the function value is multiplied maybe by 32 times 90, the same function value. So if we want to have a fair comparison of the functions, we have to adjust, and that's what we do here. Then we get a result, and then we can check how did they perform. So let's run that code, and we get the following answer. This is the result from the trapezoidal rule. And remember, if we have that kind of function, not a continuous one, a one with a lot of kinks, then most likely the trapezoidal rule is not worse than the others. Is that true for that example? Let's check. Minus more or less 7 times 10 to the power of minus 4. This is more, so Simpson is worse. This is more, so the cubic formulas are worse. This one is worse. This one is not worse. This one is a little better. This one is worse. This one is more or less the same difference. And this one is worse. So the trapezoidal is one of the best. So remember, for this type of function, trapezoidal is a very good idea. And it's not necessary to use a more sophisticated algorithm. Okay, let's come to our second example. I did only one thing different as I did above. I'm using 1 as the starting point and all the rest is the same. So if we run that code, then we are talking about a function which is continuous. Yes, it's continuous, no jumps, but there are kinks, so the first derivative is not continuous. Okay, if we run that code, then we get this answer. Now the trapezoidal rule is also okay. It's not worse than the others. It is worse a little, but very slight difference. They are all more or less equivalent. The most is a factor of 2. Here a little more than 2. Now here's the best. This is factor 3 more or less. They are all more or less equivalent. And again, I want to state, in situations like that, there are kinks and you don't know the position of the kinks, or you ignore the position of the kinks, then you can use the trapezoidal rule. If you would integrate from one to that, plus integrate from that, and so on, then the situation is completely different. Then trapezoidal is no more the best. So let's try to adjust the code. But now we are evaluating at a lot more positions. So length of section is in that case 8. So we have 7 parts. So let's use 840 divided by 7 is 120 deg. That might be not a natural number, so let's say seal. Sometimes he gets 1 point more to evaluate. Let's forget about that. Okay, and then we have I think that's it. So let's run that code. No. Okay, maybe now. And now we have that situation compared to okay, I destroyed the code above. And what do we see? Here we see errors in the range of 5 times 10 to the power of -4. And here we see better values, but not a world better, but a little better. Always a little better. Compare these two numbers, compare these two numbers, a little better. A little better, a little better, a little better, a little better, and a little better. Yes, we improved, but I expected more improvement. But so we see splitting the interval is it's a natural idea if you know the position of the kings and if you know the position of the chumps. Let's go to our third example and run that code. And we are talking about that function. It's infinite many often differentiable, some oscillations. Okay. Then we have the following situation. Which one performs best? And to my own surprise, it gets better and better. What I expected was that the degree 3 or 4 formulas would be the best ones. And I did not expect that the degree 8 or 7 formulas or 6 formulas are that good. So normally in lectures about numerics, you get the advice, don't use too high degrees. It does not help so much, but obviously in this example, this advice is not really correct, to my own surprise. Then let's talk about the last example. It's the superconvergent case for the trapezoidal rule. And what do we see now? This is a periodic function, infinite many often differentiable, and the length of the integration interval is 1 period. And if we do so, then all the formulas are more or less equivalent. So in this case, it's obviously true that the trapezoidal rule cannot be improved by other rules. In this example, all degrees will produce more or less the same result. So the trapezoidal rule performs well in that situation. So I hope that I gave you some impressions about the application, about the difference of the algorithms and how they perform. As I said, normally the advice is use Newton-Cotes of degree 2, 3 or 4, but don't use Newton-Cotes of higher degrees. And one advice at last, Newton-Cotes of degree 8 and higher it cannot be recommended because of the negative weights. And negative weights means we have cancellation, and the sum of the absolute values of the weights get 3 or 4 for larger degrees, and that's not a good idea. The sum of all weights is always 1, and if all weights are positive, then the sum of the absolute values is 1 as well. But if you have negative weights, then this sum increases, and that's not a good idea, as I said, due to the cancellation effect. So This advice is clear. Never use Newton-Cotes values for degrees 8 and larger. Only the degrees from 1 to 7 are the ones you should choose out of them. And which one do you choose? This is up to you. Maybe you have a set of problems and then you can do the check as I did here, which one performs best. Okay, and one very last point. When we found the formulas from the theory, it's clear that if we have the Newton-Cotes formulas for degree 2, they are exact for polynomials of degree 2. But what do you expect? That it's not exact for degree 3. And to my own surprise, one of my students checked and then he said, no, the formulas for degree 2 are also exact for degree 3 polynomials. And the formulas for degree 4 are also exact for degree 5 polynomials. And why is that true? Here is the reason. Then I thought about that and this is the answer. And I hope that if you're interested in, you can understand what I wrote. I don't want to go too much into the detail, but a student asked me and so it was my job to give a good answer. Okay, so this was our last video about the numerics of the Newton-Cotes formula, and the next video will be about Gaussian quadrature. Some ideas of Newton-Cotes we will use there again, but there will be one super idea on top. That's the content of the next video.